Hey, good day. Today we're looking at rectangles and squares. And why here? Why are we doing this? Quick story time. I was doing a workout this morning, and I listen to podcasts a lot of the time when I'm doing that, so I can get some more information. It's kind of lame. My wife yells at me. She likes to listen to music, and even some of the music I listen to, I guess, is too slow paced for her. So different preferences for different people, certainly. But I was listening to this gentleman speak on a topic on which he was an expert, and I was struck by how well he knew the material, right? And so sometimes it is good just to know. I know we live in an age of all this technology, and I love the technology, right? Love it. All this information at my fingerprints. I saw a cartoon the other day, and it was like, hey, before Google, if you had a question, then you were just stuck with that question, right? And what a great age we live in, where, like, if I'm watching something and I get a question about something, I can just Google it and get some information about it, and that's exciting. But sometimes it's good just to know. So, like, if I was talking to someone and I asked them what the capital of Michigan was, and they said cheeseburger, then I might think that person, was a little bit off, right? Sometimes it's good just to know. Alright? So, rectangles and squares, let's look at some properties here. Sometimes it's good just to know these properties. Alright, and I'm just going to start over here. Okay? And actually, I'm going to model a little different problem-solving strategy today. Sometimes there's clues in the question. Okay, so like I started this and I was like, well, that's 54, and I know this whole thing is 90 because it's a rectangle. I know that property of a rectangle. So I go 90 minus 54 is 36. So I knew that, right? However, I looked at that and I was like, well, is that 90? It doesn't really look like it. It could be. I'm not sure. I come back to that. Is there any other properties? I think if this is 36, that's alternate interior. That's going to be 36. Still, I need one more to make it a triangle. Wasn't really sure. So then I started going through these questions. So sometimes there's a reason to why they're ordered the way they are. So BCD right there is 90. And then it goes to 1. And then I'm kind of looking at this, and then I remember from yesterday there was some isosceles triangle pieces to some of this. So I was like, well, maybe this is 54. So I just assumed that was 54, right? Just an educated guess. And I had a math mentor, or I should say I still have. I don't talk to him as much as I should, but I have a math mentor who says if you're going to be good at math, you got to be good at guessing, right? So we're using an educated guess, and we're going to see how that works out. And if it makes sense, then we're good. And if not, then we got to adjust. So 1 is 54. We got 2's 36. 3. So if that's 54, which I'm just assuming it is right now, then I can get 3. Okay? And I'm pretty sure those are going to be the same, so that 54 would make sense. So already it's starting to make a little bit more sense. So to get 3, I go 180 minus 54 minus 54. So 180 minus 108 is 72. Alright, so if that's 72, then I should be able to get 6. And 72 would be 180 minus 72, which would be 108. And now that's starting to make more sense because we had the exterior angle theorem, so that's making more sense already. And then if this is 108 and that's 36, then this should be 36. So now I've got two isosceles triangles, which again, I'm thinking these diagonals are going to be bisected. So I really think strongly I'm on the right track. And then if this is 54, that makes that 54. Okay, so then let's just fill in what we know. 72, 4 is 36, 5 is 54, 6 is, where you at, 6, 108. And then AE is right here, and I look back up in here, AC is 18. So each one of those is going to be 9, and DB, the whole thing would be 18. Alright, so that's a good model. Sometimes there's question clues. Sometimes we got to make assumptions and work backwards and work through things to validate our argument. And there's value in that for whatever you're doing. I mean, you're going to have arguments you got to make in your life and decisions you got to make, and this helps you make rational decisions, which is a good thing. So let's go down to this piece down here. GHKL and its diagonals form 4 congruent triangles. So what it's saying is these 4 triangles are congruent. Those just don't look congruent to me. And then remember, we can't assume that this is a perfect scale, so we're just assuming it's a rectangle that's not a square. So I can kind of use this as a model, this one up here, because it's another rectangle that's not a square. And I'm pretty sure that these 4 triangles aren't congruent. Looking at. So I'm going to go roll with false. Now this says it forms 4 isosceles triangle. I'm comfortable with that after what we saw here with the angles and how that worked. Remember, isosceles triangles, the sides are the same, and then those base angles will be the same as well. So I'm comfortable with that. 1 is the same as 2. And again, I'm going to reference this one we did up here. 1 is the same as 2 is pretty much the same as 54 and E. Right? Are those the same? Well, if this is 108 here, this is 108 there because those are vertical. And using this as a model, I don't think those are the same. So I'm going to go with false there. Now GHL is this triangle, and KLH are those 2 triangles. To me, those, you just cutting a rectangle in half, the 2 triangles are going to be the same. I'm pretty comfortable with true. GK being a line of symmetry, that means I can fold it, and I don't think so. And again, I'm going to reference this guy. If I folded it on that, I don't think it's going to match up perfectly. So I'm going to go false with that. GML and HMK, now those look like they're the same. Right, we got that. So I would say true to that. And then GK and HL, those diagonals I think are the same. Okay, so that's that. I didn't really do this top thing before I hit record, so I'm a little hesitant to do it, but I can hit a little bit of it. It says property is always true. Is a parallelogram always a rectangle? So all I have to find is one counterexample, and I can think of parallelograms that look like that are not rectangles. So I'm going to say false. I'm going to say false. I guess I just need to check the ones that are always true. So rectangle is always a rectangle, and square is always a rectangle, because the only definition of rectangle is 90 degrees, and then each pair of sides has to be congruent. So figure let's go up to this one. Figure has 4 congruent sides. Rectangle is not true. Parallelogram is not true, because I can draw one that's like this, and those sides aren't congruent. So, but rhombus, the definition of rhombus is all the sides are the same, so that's true. Rectangle is not true. Square is true. Okay, so that's a little bit of that. 4 right angles, no, no, yes, yes. So you can work through some of that. Okay, that's really all I have for this today. We will practice it and keep working on it, and play it forward from there. Thanks for your attention. We will catch up soon.